So hello everyone, welcome back to Complex Differential Geometry. Today we are finally going to be doing Dolbeault Cohomology, and this is a topic I've been waiting to do for a while because it was one of the things that actually inspired me to do this course. We'll get to that in a little bit, but first of all, let's recap what we've done so far in the past few lectures to connect to what we're going to do today. Um, in lecture 5, we talked about almost complex manifolds. Almost complex manifolds. Manifolds, if I can spell that correctly. Almost complex manifolds, and we looked at the almost complex structure. I'm just going to write it in brief. That was J twiddle or J tilde. Um, and we did this whole bottom-up construction of how do we get a complex structure on a manifold by looking at the individual tangent spaces and applying a complex structure on each of the tangent spaces, and what is the minimum that we need to do in order to stitch them together, right? That was what we did in lecture 5. In lecture 6, we looked at these tools called exterior differential forms, exterior differential PQ forms. We established that on any almost complex manifold, you get this bigrading. It's called a bigrading because it has P is a grade and Q is a grade, unlike real forms which only have one grade. Complex forms can actually be decomposed using that thing that we that result that we got from lecture 3, which is V star O cross C is isomorphic to V1, I should say V star 1 0 plus O plus V star 0 1. We use that and we then generalize this to P0, and we generalize this to 0Q, and that gave us this bigrading. These are extremely useful, and so in lecture 7, we were originally supposed to do Dolbeault Cohomology in lecture 7, but I realized that we needed some more tools in order to properly talk about cohomology and the rest of the course. So we have orientations and integration is what we did last time. The main idea was how do we define integrals on the manifold, and the problem or the obstruction, let's say, and this is going to become very topical, obstructions. The obstruction to defining integrals on the entire manifold was that what if we, it's the obstruction that we have every time, which is that there's multiple coordinate systems, right? And because the coordinate systems are not real, quote unquote, they're a fiction that we put on the manifold. We need to make sure that all of our results are independent of coordinate systems. And so even if the integrals all agree because of coordinate transformations, if their determinant is negative, they will flip between what are called orientations. And so we needed a way to define a consistent orientation on the manifold. Consistent orientation. So that's what we tried to do. We did a bottom-up construction where we tried to define an orientation on a vector space by defining something called a volume form on its dual space. And then we said that, well, the orientation of the dual space is also the volume given by the volume form. And we defined this equivalence class that basically like plus and minus. So these were our two orientations, and we needed to define a 1-1 tensor field, or rather, we needed to define a tensor field that would give us an orientation on the entire manifold. So this would be a smooth assignment, I'd like to remind people that a field already implies the smoothness, so that's why we know it's a smooth assignment. Smooth assignment of orientations. And so this is what would allow us to define integrals on our manifold, and using integrals we defined Stokes theorem. Stokes theorem. Stokes has the S in his name, so I keep forgetting that. Stokes theorem. I'm going to repeat it here because it's going to become relevant now. The integral of m on a manifold M of d omega is equal to the integral on the boundary of M of its, let's call it its antiderivative. So informally, so what you would say is that d omega is the exterior derivative of omega. So you could kind of consider omega to be the antiderivative. But this is what it says. And this is a statement that is fundamentally a geometric statement. It says that you can figure out the flow of some surface through some surface either by looking at the net flow over the surface, or you can add up all the little flows on the inside, on the interior of the surface, and or on the volume that's being bounded by the surface. So as long as the surface is closed, right? This has to be a closed surface. So because it's a boundary. And this is going to become very, very relevant here in cohomology. So now that we've established all of this, we can now talk about cohomology, which is to do with detecting. So cohomology. In fact, let me say it like this: homology is about detecting holes, detecting holes in topological spaces in general. You don't need a manifold, you just need a topological space. Just like how contravectors and covectors are dual to each other, homology is dual to cohomology, but I mean, you tend to pronounce it as cohomology. And you would think that, okay, well, if they're dual descriptions, in some sense, they're describing the same thing. But in fact, you get a little bit extra for free. Cohomology tests for more than just holes in topological spaces. It tests for something called obstructions. Now, in the case of so we're going to look at two cases. We're going to look at the real case, real, and we're going to look at the complex case. There are two reasons for this. Firstly, where the real case is simpler than the complex case. So being able to identify the patterns in the real case will allow us more easily to identify the patterns that are more subtly present in the complex case when it's going to get more complicated. The other thing is that the real case, it has a simpler interpretation for what it's detecting rather than the complex case. So we're going to look at, so in the real case, we find something called a topological obstruction. And a topological obstruction could be a hole, but it could be something else as well. We might get into that into it more as the lecture continues, but one thing is, for example, your cohomology could detect the fact that, for example, on a Mobius strip, uh, that it's not orientable. That's a topological fact, and that is actually also captured by this idea of a topological obstruction. In the complex case, this gets even stronger, and it's stronger because of the complex analytic structure that we have on the complex manifold. If you've you spent any time in complex analysis, this idea has been hammered home into you that um, the complex calculus is much more strongly um, refined or constrained. Constrained is the word I'm looking for. It's much more strongly constrained than real analysis. There's not many functions that are complex analytic compared to the number of functions that could be um, compared to the set of functions that could be real analytic. So um, these are so the complex cohomology talks about complex analytic obstructions. So it's a lot stronger, and we will see how these are not just holes, but they're also a lot of other things. And in general, I'll spoil it right now. They are obstructions to um, uh, homotopic invariants. Homotopic invariants have everything to do with closed loops, or loops, doesn't necessarily need to be closed, I suppose, and how they can contract on a manifold. And that has, as we'll discover, that has a lot to do with how we discover quote unquote holes on the manifold. But they can also be used to discover other things. So that's the reason why we're using the word obstruction rather than hole, because it could be something else. Okay. So let's first, before we get into the rest of it, let's talk about obstructions. I know it sounds like we've already talked about obstructions, but so far I've just given you an intuitive idea. So what are obstructions? In our case, an obstruction is a global topological feature of our manifold, where we're going to, even though cohomology in general is defined on topological spaces, our cohomology, Dolbeault cohomology, is only possible on smooth manifolds. So whenever we would say topological space, I'm just going to say manifold for simplicity, so that I remain accurate. I mean, I don't know if the things that we're saying are true for general topological spaces, but they're definitely true for manifolds. General topological feature of our manifold is that prevents a local solution to an equation. This is where the algebra part of it comes in, to transfer or patch up to a global solution. And we're going to look at exactly which equation we're trying to solve. In the case of in the real case, we're going to be trying to solve an ordinary differential equation, and in the complex case, we're going to be solving a partial differential equation. So we're not actually going to solve the partial differential equation, just for the record. That's out of scope for this lecture. But right, so the real case is called de Rham cohomology. De Rham cohomology. And in this situation, we would like to solve the equation omega is equal to d alpha, given that, well, globally, as we said, a global form, omega, that is the exterior derivative of some other form. Given that d omega is equal to 0. Now, for this question to be well defined, every omega that is, like, whose exterior derivative is 0 has to be possible to, I mean, basically what I'm trying to say, to make it a little clearer, is that everything in the solution set of this, or in the solution set of this first equation, let's call it equation 1, has to be a subset of equation 2. Remember, I was saying that d squared equals 0 is going to be very important. Well, d squared equals 0 is exactly what tells us that this equation is going to be that this subset relationship is true. So let's see what that means. Is that like well, if omega equals to d alpha, then we get d of d alpha is equal to 0. So unless d squared is equal to 0, this wouldn't always be the case, right? So therefore, there could be solutions to this. Basically, what I'm saying is that let's say that this is 2. If we had something like this, where this is the solution set of 1, then this question would be ill-defined, right? So we need instead for it to look like this. So what is 1 and 2? We're going to get into what 1 and 2 are in a little bit. I'm trying to avoid saying their names because I want to say it in later in the Durham section. So with all of this defined, so these are the equations that we would like to solve for the real case, and this is what makes this question well defined. If we fail to find a solution for this globally, then we get something called a topological obstruction. Or the failure of this equation to have a solution for a particular form means that there is a topological obstruction of a certain kind. And depending on what kind of form it is, it's a different kind of topological obstruction. We'll talk about that. So, and then we have Dolbeault cohomology. Dolbeault cohomology. Very similar, and this is where we're trying to like leverage the analogy. We already know the Dolbeault operators, right? So we're trying to solve omega equals to partial bar of alpha, given that partial bar of omega is equal to 0, right? And what makes this well defined is partial bar squared is equal to 0. This gives us the same relationship that we had before. It says that the solutions to this equation are a subset to the solutions of this equation. So the idea that, oh, what are the solutions given that this is true, is a well-defined question to ask, right? So these are the fundamental solutions. And so this idea of obstruction is essentially this local to global elevation, is that what it's obstructing is the process of raising it to the global level. That's what it means to be an obstruction. Here it's a topological obstruction. Here it's going to be a complex analytic obstruction. And the clue for why this is a complex analytic obstruction, which will become more clear as we keep going, is that D decomposes to partial and partial bar, which means that the holomorphic and the anti-holomorphic sectors are kind of being treated differently, and each of them has their own operator on them. So that might give us a clue why the complex analytic structure kind of comes into play here. So now we're going to talk about Durham cohomology, partially because I want you to know about Durham cohomology, but also because it will help us understand the way that Dolbeault cohomology is working. Okay, so let's talk about Durham cohomology. And the key thing to remember here while I talk about all of this is the de Rham cohomology and the Dolbeault cohomology are the real and complex analogs of each other. So keep in mind all of the definitions that I'm going to be giving right now so that we can transfer them over to the complex case. So now we're going to take these mysterious equations that we just wrote over here and we're going to give them a form, or we're going to give them names. So let's say that we have the equation d omega equals 0. If omega satisfies this, if omega is a K form, then we call omega a closed K form. In this case, right now, whenever I say form, you'll know that I'm talking about a differential form. We're no longer, I don't think anywhere in this lecture we're going to be talking about exterior form. So every form that I mentioned here is a differential form. We're going to be using the exterior derivative. In order for the exterior derivative to be well defined, it has to be a differential form. It has to have that smooth structure on it. So, right. Or it has to be a smooth section, I suppose, to be more precise. So we're going to call the set of these closed forms zk on M, and this is going to be defined as the kernel of the exterior derivative operator from omega k of M, the smooth or like the differential k forms, to the differential k plus 1 forms. The reason I'm mentioning this will be these orders will become apparent in our next definition. So this is called zk, and this is it's a vector space actually because you can add the forms and so forth. So this is the set of closed k forms. The interpretation of closed k forms comes from the Stokes theorem. So if I have if I try to evaluate a closed form on a boundary, what happens? Um, Stokes' theorem tells me that this, so let me say that here, this is Stokes. Stokes is helping me out here. So d omega on M, right? So the form on the boundary, the integral of the form on the boundary is equal to the integral of its exterior derivative on the interior. But this integrand is 0, right? So this is equal to 0. So what it tells us is that closed forms will evaluate to 0 on the boundary. So closed forms, or more precisely, closed forms evaluate to 0 on closed surfaces. So that's why they're called closed, is because they evaluate to 0 on closed surfaces. They allow us to detect if a surface is closed. So the next thing that we have to define are exact forms, which are referring to the other equation, which is that if there must exist an alpha such that omega is equal to the exterior derivative of that alpha. So what does this mean? Well, okay, well, first of all, omega, we say that omega is a K form. And then in that case, if this is true, then we would call this, if this is true, then omega is an exact K form. And we'll get to the what exact means in this situation in a little bit. But so let's define the set of all of these exact K forms, right? So we call that Bk of M, and it's defined to be the image of d of omega k minus 1. See, this is why I was saying that we needed to specify the exact derivative operator, because k minus, this is not the same one as the one we defined last time. So then that goes to omega k of m, right? So if we think about what is the set of all of these forms that would be exact, all of the exact k forms, well, on our manifold, right, for this to work out, alpha would have to be a k minus 1 form, right? So that the exterior derivative would give us a k form. So then, in order to get the image of all of the exact k forms, we would need to take all the k minus 1 forms that we have on the manifold. Each of them would give us a valid exterior derivative, and that exterior derivative would give us an exact k form, right? So the image of the exterior derivative on the k minus 1 forms must be the set of all exact k forms. So that's why we have this definition over here. So now that we've defined the exact k forms, let's see why this works. Well, okay, so if we evaluate this exterior k form, this exact k form on the boundary, what do we get? Well, we know by Stokes' theorem again. So Stokes' theorem that this is equal to its exterior derivative when applied on when evaluated over the interior of that submanifold, right? So we don't know that this is 0, right? Because this is not, we don't know if it's a closed form. So, but we do know that there exists some alpha such that I can rewrite it like this, right? Which this is d square alpha. But d square is equal to 0. It's the 0 map, right? So that means that this is 0. But if this is 0, right? If this is 0, then this is 0. I mean, we didn't actually change anything else. We just rewrote the integrand. That means that every exact form is a closed form. This is going to become very important. So, but think about what actually allowed us to say that. What allowed us to say that was the fact that d squared was equal to 0, right? That's what allowed us to say that this was 0, which allowed us to say that this was 0, which means that d omega is 0. That's what, so basically what I'm saying is d squared is equal to 0 implies the statement, right? The whole statement that d square alpha equals 0 implies that, or this is what I want to say. Exists alpha, omega is equal to d alpha implies that d omega is equal to 0, right? So this is what actually allows us to say that this set BKM is a subset of ZKM. We'll revisit this. So let's now try to interpret what we're trying to do here in an effort to reveal the cohomology group, right? So in order to do that, I'm going to draw an annulus. An annulus, this is kind of an oblique angle. We're looking at it from the top and slightly in the front. So an annulus is a disk with a little hole in it, and we're going to be detecting this hole. So first of all, we have a closed curve, right? So this is something that's detected by elements of Znk or Zk of M, right? And why does this detect a hole? Because the inside of this is not a submanifold. Because a submanifold has to be topologically. So if I use a different color here, think about this inside region, right? Let's redraw it here. This inside region looks like this. This is not homeomorphic to R Rn, or in the complex case, it would be Cm, right? We're still talking about the real case, so let's just say Rn, because Rn definitely doesn't have a hole like this, right? So there's a rigorous proof you could do for an annulus or for a space like this that would reveal that this is not isomorphic, but like intuitively we can understand that this is not isomorphic to Rn. So this in the inside cannot be a submanifold. So this is not a submanifold. So what this reveals actually is that the annulus, in a topological sense, the annulus is not simply connected. And so it has something called non-trivial homotopy. Hard to pronounce. Homotopy. Yeah, there we go. Non-trivial homotopy. There we go. So what does that mean? That means that there's a curve, there's a closed curve that we can't contract into a point. The thing that's preventing us from contracting into a point, the thing that's preventing us, an obstruction, is the hole, right? But right, so this is where that idea of the hole, detecting a hole, comes from. Detects a hole, right? So this curve, this blue, it's an element of ZKM, but it's not an element, not in BKM, right? So that's why what we want in order to detect holes is to detect curves that are in ZKM but not in BKM. That's our main idea. So let's contrast this, right? Let's contrast this with a different curve. Let me use a different color here. Let's say I drew this curve, right? This is closed. So this is in ZKM, right? And in fact, I don't need to use K here. We know the dimension. So this is actually, this would be Z1, this would be B1, and this would be Z1, right? Okay, so notice that what's inside here is an open set. This is isomorphic to Rn. So this is bounding a submanifold, right? This is the boundary of some submanifold. So this is both an element of Z1m, and it's also an element of B1m. And that's precisely what tells you that there's no hole inside. Okay, so this is like one way to use the homotopy group in order to, and the homotopy group is this group of these curves, right? The curves and like whether or not they can, like that are classified whether or not they can contract into a point. And so these definitely detect holes, but when we move from the uh, the quote unquote homology way of thinking about it, which is thinking about the curves directly, to thinking about them in terms of the differential forms that detect those curves. Remember, we went here. This is how Stokes' theorem is telling us how an exact form detects a boundary, right? It detects a closed curve that also has an existent alpha, right? There exists some alpha, and this exists alpha is what tells us that this is a boundary, right? For a normal, for any old closed form, d omega is equal to 0, sure, it's closed, and sure, for an exact form, it also always will be a closed form. But for a generic closed form, we never know if there exists any alpha. I'm going to say question mark exists alpha, right? So if this is true, then we also have an exact form, which is what is telling us that there's a boundary. And that's why we need to solve both of those both of those equations at once, right? For omega, so that we can so that we have and if we are able to solve them, then we have something that there isn't a hole. If we fail to solve them, that obstruction is what tells us that there's a hole. So that's the way in which the algebra viewpoint and the cohomology, the differential form viewpoint, are kind of coinciding. And the power of the differential form viewpoint is that it can use the information of the homotopy group to actually tell you other kinds of obstructions, not just holes. It could also maybe tell you if the manifold is twisting or if the manifold is orientable. We'll get to that in a little bit. So this brings us to the kth DRAM cohomology group. So there are multiple of them, one for each k. DRAM cohomology group. We basically outlined the principle already, so I'm just going to write out the definition. It's called K, sorry, the K should be on the superscript, HK dr of M, and it's defined to be the quotient group of ZK M by BKM. So for anyone who's unfamiliar with quotient groups, because we haven't bespokely covered group theory, all this means is that we take every element of ZK. Let's say that we have a form Z in ZK, and we can say that it's equal to some closed form C. I'm breaking my rule that forms are named after Greek letters here for a little bit, uh, plus an exact form E. So we're sending all of the elements of B into to 0 when we take the quotient group. So what this basically means is that this is 0. So we only have the part of the closed form that's not exact, right? So that is what we're saying. So every exact form goes to 0. Every form that is that has an exact part plus a remainder, the remainder stays, but the exact form part goes to 0. So what we have left is all the C's, which are these are elements of ZKM that are not elements of BKM. Right? That's exactly what we wanted. These are the so-called non-trivial forms. So what is C? C is a differential form that detects a closed curve that we know for sure is not the boundary of some other submanifold. We know it's a closed curve because it's an element of ZKM. We know that it's not an element of BKM, which means that it's not the boundary, it's not detecting something that's the boundary of any other submanifold. This indicates that the form has detected a loop that cannot be shrunk into a point. It's detecting the fact that the curve is detecting the fact that the manifold is not simply connected. And so basically these forms are machines that are allowing us to detect the topological obstructions to of simply connected curves, right? So that is how cohomology is helping us detect these things called topological obstructions. But as we'll get to it in a little bit, these topological obstructions need not be holes, because the fact that the loop cannot close can tell us, or the differential form that's detecting that the loop cannot close also detect some other things, and that will allow us to find other types of topological obstructions, kind of like what I was alluding to before with the Mobius strip, where one of the DRAM cohomology groups is going to detect the fact that the Mobius strip is non-orientable. Right. One last thing about the DRAM cohomology group before we move on is that we call the dimension of HK dr M this is defined as bk, or b, I guess you would put it as a subscript. It's not covariant or contravariant. This is just a scalar. This is called the Betti number. And we're going to interpret all of this in a moment. But first, we will look at some more important um, concepts about the de Rham cohomology group. So that being the chain complex. Chain complex. So a chain complex is a sequence of vectors. In our case, vector spaces. It can be any abelian category, but since we are not talking about category theory, I'm just going to define it over vector spaces for now. So um, there's more stuff coming here. So we got, let's say we have this vector space vk minus 1, then we have vk, and then we have vk plus 1, and then dot dot dot. There could be more. Let's call this map fk minus 1. Then we have a map fk. This is called a chain complex if for all these you know um, sequential maps, you get fk minus 1, or sorry, fk after fk minus 1 is equal to 0. And this should start ringing some alarm bells because this should look familiar. And this has to be true for all k in the chain. So the idea that this condition kind of implies is that the image of fk minus 1 is a subset of the kernel of fk. Oh, that seems familiar. We looked at images and we looked at kernels. So this kind of like the chain complex that we care about is called the de Rham complex. De Rham complex. And the de Rham complex talks about this chain. I'll explain what all of these symbols mean in a little bit. So this symbol means that, okay, so first of all, here it says that the image of fk minus 1 is a subset of the kernel of fk. So the first arrow pretty much just means that this is an injective map. Injective map. And the last arrow means that this is surjective. Right? Because the image has to be a subset of the kernel. So the kernel is the subset of the domain that maps to 0, and the image is the subset of the codomain that is mapped by the entire domain, right? So, okay, so I noticed that my explanation for why there are zeros on the two ends of the de Rham complex isn't very satisfactory. So let's kind of re-explain why this is true. I just said that this is injective, and then this is surjective, and then I hand waved it away, and that wasn't very satisfactory. So let's see what the actual explanation is. So the thing that makes this a bona fide complex is that the image of each of the maps fk minus 1 is equal to the kernel of the next map. What does this mean? Well, let's think about what an image is and what a kernel is. So let's say that this is C, this is D, the domain. This is C, the codomain. So the image is exactly the subset of the codomain that is mapped by the entire domain, right? Let's say that that's fk minus 1. And let's do the same thing for the kernel. So for the kernel, so again, this is the domain, this is the codomain. The kernel is, so we have this 0 element in the codomain, or the identity element, let's say. It's the subset of the domain that maps to that single identity element, right? And what we're saying, oh, sorry, this shouldn't be equal. This should be subset or equal, right? So we're saying that each fk minus 1, the image of that map, so when it maps to here, that map has to map into a subset or the entirety of this. Yeah, so what we're saying is that this blue guy here and this yellow guy here, this has to be a subset or equal to this, right? So what does that mean here? That means that I of the identity element is equal to the kernel of I. And in abstract algebra, you can prove that if the identity element is mapped to the identity element, then the map is injective. And so on the other hand, on this side, what it's saying is that the image of omega m of m is exactly equal to the identity element, right? And which is, or yeah, the is exactly equal to the kernel of D on like, let's say dm, the D acting on the M forms. So M forms being M manifolds, right? M manifolds, the maximum forms you get on them are M forms. So this is saying that this is saturates this subset or equal to. It's not a subset, it's exactly equal to, which means that the upshot of both of these is that this terminates at the beginning or at the start, and it terminates at the end. In other words, the complex is finite. Is finite, or let's say finitely long. Remember that the way that we defined complexes is that we said dot dot dot, arrow, then we had a vector space vk minus 1, arrow vk, arrow vk plus 1, arrow dot dot dot. Then we had a map fk minus 1, then we had a map fk, then we had a map fk plus 1. This would be fk minus 2, right? So in general, these dot dot dots or these ellipses means that it could be infinitely long. It could never end. But the idea is that with the de Rham complex, this is, I'll write it here, this is finite. And we expect it to be finite because we want there to be at least 0 forms and at most m forms, right? So this makes sense that the de Rham complex is finite. So now we can go back to the main recording. Here, the consistency condition of the exterior d square equals 0, d square equals 0, is exactly this equation, right? It's d after d is equal to 0, which means that this is a bona fide chain complex. And what that means is also that thing that we were saying, right? The subset thing, which means that zk, which, right, bk, let me put them right underneath so that it's more apparent what I'm trying to say. bk of m is a subset of zk of m. So this idea of trying to find all of the exact forms that are closed forms is a coherent question because of the fact that this chain of maps. So this is just us repeatedly applying the D operator on a bunch of manifold or on a bunch of forms, right? That means that the existence of this chain complex means that this question is well formed, and that this is the significance of the fact that d square has to be equal to 0, because otherwise we couldn't even talk about this chain complex. And so therefore bk would not be a subset of zk of m. And so us trying to find find these special forms wouldn't be a well-defined question. And why is that a problem? That's a problem because otherwise we wouldn't have uh, like the geometry would just be inconsistent, and therefore we wouldn't be able to um, ask this coherent question about the space. So um, the interpretation of this is, so D is kind of like gives you the boundary of or it's the cohomology dual to the boundary operator, right? The boundary operator is usually called partial. Confusingly, the Dolbeault operator is also called partial. So this is called the boundary operator, and this detects or this on a chain will give you the boundary of that chain, but the cohomological dual will give you the form that detects that chain. So it's not the boundary, but it is it tells you the existence of a boundary by giving you a machine that detects that boundary. So it gives you a form whose existence detects a boundary. And so therefore this fact corresponds to the idea. Sorry, that was a little convoluted, but that is kind of how cohomology works. I mean, if we were doing homology, a lot of this stuff would be easier to explain. At every step you have to remember what we want to talk about are curves, but what we're using are, even though they're very powerful, are machines that detect those curves. So what I really want to say, to keep it simple, is that we have a curve, a closed curve that is exact. But what I need to say is that we have a machine that detects a closed curve, which is also a machine that is exact. So that's why it gets all complicated in cohomology. Um, but the trade-off is that the result is more powerful. We get more we get more obstructions than just holes, even though we're motivating the examples using the analogy of using holes. So without further ado, without me giving any more caveats, what this means is that the boundary of a boundary is always 0. This is the geometric consistency condition. What does this mean? Well, let's say that I have a bounded manifold, right? We talked about bounded manifolds in our lecture 7 on orientations and integration, because we had to talk about Stokes' theorem, which was in fact a setup for this. So um, let's say that we have a disk, right? This is a disk. If I try to find the boundary, then I will get this submanifold. It's going to be and if the disk is an M manifold, then the boundary is going to be an M minus 1 manifold. But notice that the boundary of a disk is a circle, and the boundary of a circle doesn't exist. This is just an example. This is not a proof. But this should give you an idea of why we expect this to be true. You can keep doing this for various different geometric objects. You'll find that if an object is filled, its boundary is such a surface which itself never has a boundary. And because of this fundamental geometric condition, that like the okay, let me say it this way. The fact that this geometric condition is so fundamental to geometry corresponds to the fact that d square is equal to 0 is even required, is required to even ask the question of what are my DRAM cohomology groups. So basically, if all of that was a little bit too abstract, if this thing doesn't exist, then there are no well-defined cohomology groups. And the cohomology groups, which we're going to get to right now, we've already talked about the local to global patching issue, right? So what the cohomology groups tell us is that, so the kth cohomology group, the real cohomology group, it tells us whether we have global solutions to there exists alpha for omega equals d alpha, such that, or like given that d omega equals 0 um, for real manifolds, in the case of real manifolds. So the idea, the interesting thing about in de Rham cohomology, and there's going to be an analog for this in Dolbeault cohomology, is that this is always true locally. Locally, you have something called Poincaré lemma, or Poincaré's lemma, which says that locally every closed form is exact. So if you thought about the local version of Zn, or sorry, Zk mod Bk, this would be trivial, because uh, because of Poincaré's lemma. When you try to take that up to the global setting, that's when you get problems, because maybe you can't define a form globally, a K form globally that will satisfy those conditions, that it's a closed form that's also exact. If there is a form like that, that tells you that there's some sort of topological obstruction. So that's the link between the Dolbeault cohomology, that's the link between the de Rham cohomology group and this local to global patching picture that we had so far. So what does the de Rham cohomology group actually detect? Sorry, what does the de Rham cohomology group does the de Rham cohomology group detect? Well, an oversimplified answer is it detects holes, right? Well, it detects topological obstructions, but it seems like it detects holes. So, for example, the group HK dr of M, the kth de Rham cohomology group detects something called a K hole, or a K-dimensional hole. So what are different dimensional holes? Well, a zero hole is the number of connected components in a topological sense. The number of one holes, these are the holes that we are familiar with. It's the hole in the center of a donut. So these are, yeah, like the hole in the center of the donut. Two holes are cavities, like the inside of a sphere. In general, a K-hole is a void in a manifold that is surrounded or wrapped by a K surface. which is short for a k-dimensional surface. Well, a closed k surface, right? So, well, given that it has to be surrounded or wrapped, it has to be a closed surface. So that's what it means. So the hole in the center of the donut is um, is a one hole because it's wrapped by a circle, right? You can wrap the cross section of the hole using a circle, and the cavity at the center of a sphere is wrapped by the surface of the sphere, which is a two-dimensional surface. So that's a 2D hole. And there are higher dimensional holes. They're wrapped by higher dimensional surfaces, but we don't have enough dimensions to think about what those kind of holes look like. We can't even visualize a 3 hole because it would require a 4-dimensional space in order to properly visualize. So there are higher dimensional holes as well. I noticed here that I didn't really talk about uh, what these kind of different holes look like. So let's just give a brief rundown of what these holes look like. Let's say that we have a manifold like this. We haven't really drawn manifolds like this because they haven't really come up. But manifolds can have multiple components. So 0 holes are kind of like the absences of holes, right? So they count 1, 2, 3. So there are 3 0 holes in this manifold. So these are the number of connected components. And so then we get 1 holes. These are the ones that you might be familiar with. Let's draw a circle. The hole in the center of the circle is a 1 hole. So it's this gap right here. That's a 1 hole. And why did I go over there? And 2 holes are cavities. So let's say if you have a sphere, let me draw the sphere a little better. Sphere, then the the part on the inside, I don't know how am I going to like, yeah. So the part on the inside of the going in there, inside of this is the 2 hole. It's a space that's wrapped by the entire surface of the sphere. So a donut, for example, a torus, has 3 holes. It has the hole here. This is a 1 hole. This is wrapped by this circle. A donut also has another hole. I'm going to draw that in pink. That's also wrapped by a one surface, like a circle. So this is also a 1 hole. Let me color code that. So this is a 1 hole. And it also has a cavity, right? It also has the cavity that is wrapped by the entire surface. So the donut also has a 2 hole. In fact, it has 4 holes. It also has the whole manifold is one connected component, so it has a 1 0 hole as well. So that is how you kind of understand holes on a manifold. So in fact, there if we have like a M manifold, if we have an M manifold, and we're talking about real manifolds still, so then it can have up to M holes, right? M-dimensional holes, as is kind of evident from here. Like we couldn't have like a 3-dimensional wrapping on a 2 surface, right? So therefore, we would need a 3-dimensional manifold to actually have a 3-dimensional hole. So I'm now going to hand it back over to the record. So this is something that the DRAM cohomology detects. So it's not false to say that it detects holes. It's just that it doesn't detect only holes. It can detect other types of topological obstructions as well. So the topological obstruction here is the homotopy invariant of like the number of holes, which is what the Betti number actually tells you. So BK tells you the number of K holes in a manifold. and that is a topological invariant. So if two topological spaces are homeomorphic, they must have the same Betti numbers for all k, right? Um, and from the Betti numbers, the alternating sum of the Betti numbers gives you the Euler characteristic. That gets into topology territory, but I just wanted to mention that briefly. So, as with my original example, if you have a Mobius strip, the group H1dr of the Mobius strip, I'm going to call it Mobius. The fact that this is non-trivial, that's how we detect them, by the way. That if the group is non-trivial, if it's not the trivial group, that means that there's some sort of obstruction. The group being trivial means that we didn't find any exceptional forms, right? If it's non-trivial, that means we found a class of non-trivial forms that satisfies that doesn't satisfy those equations that we talked about. The failure to satisfy those equations. So this is this non-triviality represents the obstruction that we were talking about. So, or maybe I should bracket the whole thing as the obstruction. So there is a non-triviality which detects a hole in the Mobius strip. Obviously, there is a hole in a Mobius strip, but it also detects the fact that the Mobius strip is non-orientable. So this is an example of how the topological obstructions don't just have to be holes; they can also be other facts, other topological facts about the manifold. It's just that it has to be some sort of global feature that is being prevented by the existence of this group, or the group is actually detecting the existence of some sort of obstruction. So now we can talk about Dolbeault cohomology. And given that we've already talked about de Rham cohomology, we can kind of speed run through this because the structure is almost the same. And so now we can focus on just the fact that there's going to be a splitting based on P and Q. So let's define a Dolbeault cohomology. I suppose you call a cohomology a set of cohomology groups is your cohomology. It tells you the information, the data that the cohomology groups give you, right? Yeah. So let's construct the Dolbeault cohomology groups. It's really just the same thing, but we will talk about the nuances in this. We'll highlight the nuances in the complex construction. Dolbeault cohomology groups. Okay, so we use d square equals 0 to find the topological obstructions. So now we're going to use the fact that d is equal to partial plus partial bar to use plus the idea that partial bar squared is equal to 0 to define the Dolbeault cohomology groups. So just as a reminder, partial bar is a map that takes omega pq on M, and it gives us omega pq plus 1 on M. Since partial bar doesn't change the holomorphic grade, we're going to analyze the cohomology groups by keeping p constant. We're going to do that. So the way we're going to construct this chain, so we're going to construct another chain complex here, and this is going to be, this is called the Dolbeault complex. Last time we started with the intuitive picture and then we ended with the complex. But now, since we know how where the complex comes from, I'm just going to start with the complex. So it's very similar. So we get omega p0 of M partial bar. Is that p0? Yeah. So p is a constant. P1 of M should silence my phone. And then dot dot dot, and then the last one, which will be the highest grade possible, which will be PM on M. And then we're running out of space to make this chain, so let me make it smaller. I can move this over here. Right? So same idea. It's just notice that it's only Q that's changing, so it's pretty much the same kind of chain. And the consistency of this, the fact that the images are the subsets of the kernels, is going to be ensured by the fact that partial bar squared is equal to 0. So same idea, same everything. So now we just have Z, we're going to call it Z partial bar PQ on M, which is going to be the kernel of partial bar omega PQ M to omega PQ plus 1 M. Very simple. These are called the partial bar closed forms. And according to our definitions last time, partial bar closed forms are automatically closed under the overall exterior derivative. You can look at the notes. There is a part that requires that. So, and then we get this guy. And this is similarly the image of partial bar from omega, too many parentheses, omega PQ minus 1 of M to omega PQ of M, right? And then we can define the Dolbeault cohomology group. See, that was fast. Dolbeault cohomology group in the same way. So we say that H PQ. So now there are two numbers to keep track of. That's the complicated part. So this is equal to the quotient group. Same idea. I'm going to stop saying same idea. I think you get the picture. So PQ M partial bar, right? Just I'm writing the quotient as a fraction looking thing. Sometimes you do that, right? So there we go. So let's quickly like interpret what we just did here. Now we have now we're just replacing all of our machinery from the case where we had D to the case where we have partial bar be the generator, right? But now that we have two generators, things get a little bit more interesting. Although what's going to be interesting is that we only really care about the version with partial bar because of a lot of symmetries that we're going to see. So and this is where the fact that we can do this with partial bar and we can do it with partial, this is what's going to give us holomorphic obstructions. So let me find a better place to write that. Partial bar is going to give us holomorphic obstructions, and partial is going to give us anti-holomorphic obstructions. What does that mean? Well, in a way, what it means is that so let's get to the part where we're talking about the local to global behavior. So local to global patching. So we said that we were trying to solve these equations, we kind of glossed over it because they were pretty self-explanatory, but we have partial bar omega equals 0. These are the partial bar closed forms. And we have there exists alpha such that omega is equal to partial bar alpha, which are the partial bar exact forms. And these are the holomorphic equivalents of what we did with the de Rham cohomology, right? So now what we're saying is that the forms that fail to get promoted to the global version, like these are okay. So right, first of all, we had the Poincaré lemma in the real version, right? But in the complex case, we have a complex analog called Dolbeault's lemma. Dolbeault's lemma. Dolbeault's lemma says that locally every partial bar closed form is a partial bar exact form. And so we're always guaranteed to have this local solution. So when we try to promote it to a global solution, globalize it, I don't know, globalize it, the failure to globalize it for omega a PQ form is a holomorphic obstruction. Holomorphic obstruction that's captured by the group H, K, PQ on M, the PQth Dolbeault cohomology group. And similar to the Betti numbers, we have there are a set of numbers for the Dolbeault cohomology group. They're called the Hodge numbers, HPQ. HPQ is defined to be the dimension of HK-PQ of M. And it similarly tells you the number of different types of obstructions. And these obstructions have a more complicated interpretation. Let me see if I can elucidate it to some extent. The 1, 0, and 0, 1 obstructions are the failures to patch over the in some sense the failure to patch a solution of a 1, 0 form, but a 1, 0 form and a 0, 1 form. So to go from the local version to the global version, and with the higher order Dolbeault cohomology groups, it talks about more complicated failures in an effort to patch up these forms to get a global form. So it gets really hairy once you try to kind of interpret. Okay, well, the 2-0 form is like the failure to patch of patches of solutions that you've already patched up in some way. But to not get into any of that, just the main idea is that there are more and more complicated failures for there to be a complex analytic structure in a certain place. So and so that brings us to the anti-holomorphic obstructions, which there's a dual formulation to this in terms of partial squared is equal to 0, the regular Dolbeault operator, and then we can talk about partial closed forms, PQ forms, and we can talk about partial exact PQ forms. So, sorry, PQ forms. But this isn't very necessary because, or we don't really use it very often because of this fact that so the cohomology groups that you would get from here, I suppose you'd also call these Dolbeault cohomology groups. These look like HPQ partial of M instead of partial bar of M. So these give you the anti-holomorphic obstructions. Um, if you're wondering why partial bar gives you the holomorphic obstructions and partial gives you the anti-holomorphic obstructions, think of it like the fact that df dz bar equals 0 makes something a holomorphic function, right? And so what a holomorphic obstruction is the failure of some global function to be holomorphic. So we're kind of trying to solve an analog of this equation. So if something doesn't depend on the anti-holomorphic part, then it is a proper holomorphic function, right? So if it doesn't depend on the anti-holomorphic coordinates, I mean. So in a similar vein, the reason why we use partial bar to detect holomorphic obstructions is because if it doesn't depend on partial bar, then it's holomorphic. If it doesn't depend on partial, then it's anti-holomorphic. So that's the reason for the flip. And um, the reasons why we focus on the partial bar, one, is because it the partial bar relates directly to our next topic, to sheaf cohomology. We're not going to get into the details of sheaf cohomology, but because it's such a fundamental result that it's called Dolbeault's theorem, so it's pretty important. So I thought we would at least state it in this lecture. So number two, this is true. H partial PQ on M is equal to H partial bar PQ, called it G, PQ on M, complex conjugated. So since this is true, so remember, these are families, or these are collections of forms. So we know what its complex conjugate gives you. It gives you the complex conjugate of the forms, which then you have to distribute over the coefficients and so forth, and then you get yeah, for every p form you get a p0 form, you get a 0p form, etc., etc. So that's how you define the complex conjugate. I'm hand waving a little bit because it's not the main point, but because of this, they're not independent. The 1 0 obstructions are related to the 0 1 obstructions in a very specific way, right? So that's another reason we don't really have to care about the other formulation. And number three, most geometric objects are holomorphic that we care about in analysis and stuff like that. So so that's why we pick holomorphic the holomorphic version rather than the anti-holomorphic version. But if you cared about anti-holomorphic objects, then you could use the other one. Then I mean, it's there. There's nothing stopping you from using it, and the machinery is all the same. It's just a mirror reversed version of it. Okay. So the last few things. So now that we've talked about Dolbeault cohomology, we're done technically with the lecture in a sense, but now we should talk about Dolbeault's theorem, and then I'm going to show you two examples very quickly, no computations, of some examples of the Dolbeault cohomologies of some complex manifolds. Okay, so let's talk about Dolbeault's theorem, and right, and then we'll be set up for the next lecture. So Dolbeault's theorem. So Dolbeault's theorem is the complex analog very aptly of de Rham's theorem. So complex analog of de Rham's theorem. De Rham's theorem, I'm not going to write it here in full. I don't have the precise formulation, but it basically says that the de Rham cohomology is isomorphic to, well, the kth de Rham cohomology group is isomorphic to the kth singular homology. We don't have time to get into what the singular homology is. That's why we're not getting too much into it. But the Dolbeault version of this is that is called Dolbeault's theorem, and it says that the Dolbeault cohomology is isomorphic to the sheaf cohomology, which is also known as the Czech. I think it's like that. Yeah, Czech cohomology. Funnily enough, this character, I think it's called a caron. My font doesn't support it, so in the notes there's no caron on the C, unfortunately. So, and not sure I want to change the whole font of the notes just to support that one character. But yeah, it's called the Czech cohomology. And so what is the idea of the sheaf cohomology? Well, remember we've been talking about this local to global patching. Sheaf cohomology is kind of like a formalization of that in, I believe it's in algebraic topology, where you define this sheaf cohomology. So yeah, a sheaf, we're going to talk about this very roughly because we don't have time to get into sheaf theory. So a sheaf is an object. It's a mathematical object, but everything here is a mathematical object. An object that systematically organizes local data. You can see the connection here to the local to global patching idea on the manifold. It's different from a manifold. Remember when we were talking about like a vector bundle on a manifold, we were talking about these local trivializations, and then like we patch together the local trivializations in a certain way to make a manifold. A sheaf is a little bit more loose than that. A sheaf is a bunch of local neighborhoods of local data that don't have to agree in the same way in their overlapping regions, the same way that a manifold has to do in order to have an atlas and things like that. So this is a much more general space. So we have a sheaf called omega p, which is the sheaf of p forms. And it assigns sheaf of p forms. So this assigns to each u subset of M. Well, now we have the manifold structure, right? So generally you wouldn't need a manifold here, but if we have a manifold structure, you could think of a manifold as a set of points, and then if you have u subset of M, then the vector space of holomorphic p forms. So a sheaf omega p assigns to um a vector space of holomorphic p forms, right? So that's what a sheaf is, and it is what captures and crystallizes this idea of order Q uh, obstructions. So yeah, so the sheaf cohomology is HQ of M omega P, and this categorizes the order. Order is order Q is not something that's talked about formally. It's just kind of like the complexity level roughly of the obstruction is Q level, where Q is some measurement of uh, how entangled the obstruction is. I don't want to say any adjectives. It's like it's some measure of the complexity of the obstruction. So order Q obstruction. So we're just going to hand wave away that for now. Order Q obstruction. Higher Q means more complicated. To patching, local P forms or local holomorphic P forms. Let me not make this incomprehensible. Holomorphic P forms into global ones. So this is also is an obstruction, right? This is still some sort of obstruction because it's preventing us from coming up with a global solution to some sort of problem. Right, and so now I'm just going to state Dolbeault's theorem. This is going to be pretty dry, but for people who've taken or people who know sheaf cohomology, this might be a good thing to add. So for p greater than 0, where p is an element of Z, the sheaf omega p has a fine resolution and exact sequence which is equal or equivalent to the Dolbeault complex that we looked at before. And it looks like this: 0 omega p partial bar. I'm going to define these in a moment. P1 partial bar dot 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 partial bar 0. So A PQ is the sheaf of PQ of smooth PQ forms. So it's the analog to omega. PQ forms. And remember, so a sheaf is a way of assigning a vector space to a local neighborhood, right? That's what a sheaf is. So then the theorem says that, well, the theorem says that this exists, and as a consequence of this, for all p comma q greater than or equal to 0, H partial bar PQ, the Dolbeault cohomology group, the PQth Dolbeault homology group, is isomorphic to the sheaf cohomology group. So yeah, I just wanted to have this. This is Dolbeault's theorem. This formalizes, this is the formal statement So since this is all dry and we don't have any idea about what sheaf cohomology is, so um, let me try to kind of take away something that will be useful to people here. This is the formal statement that the Dolbeault uh, cohomology is actually, or actually has an interpretation as a local to global obstruction detector, because that's what the sheaf cohomology is, right? And in the case of the de Rham's theorem, uh, the singular cohomology is also telling you the same thing. The singular cohomology is about chains and it's about holes, and so it tells you that the de Rham cohomology groups are actually detecting holes in your topological space. So that's where de Rham's theorem and Dolbeault's theorem kind of come into play into this whole thing. So if you take away anything from this statement or from this theorem, it's this. It's the proof that this is a valid interpretation. So the last thing we have left to do is to talk about some examples, and I will not try to not bore you too much with these, so we're going to go through these really fast. In fact, we don't have the means to or the time to compute a lot of these things, so I'm going to give a heuristic justification. So we're going to look at CP1, the complex projective space. This is also called the Riemann sphere. Remember, we were talking about this in lecture 2. So we were saying that because we have this point at infinity that completes the sphere, and so CP1 actually is isomorphic to S2 as a real space, as a real manifold. So let me remove that. We don't really want to talk about real manifolds right now, but that's CP1. And we're also going to talk about T, and I'll call it TC, the complex torus. TC is isomorphic to the complex numbers modulo lambda, where lambda is a two-dimensional matrix. Sorry, I misspoke. Lambda is a two-dimensional lattice. We also took a look at that in lecture 2, how you can create a torus out of the complex plane and a 2D lattice. So if you want a refresher, you can go back and look at that lecture. So we're going to look at the Dolbeault cohomology groups for two of these, or these two. So H00 of CP1 is isomorphic to C. H10 of CP1 is isomorphic to 0, the trivial group, or the trivial set. I guess you could call it this. H01 is isomorphic to this again, and H11 is isomorphic again to C. This is guaranteed by Liouville's theorem, which says that global holomorphic functions have to be constant functions. So because 800 is talking about zero forms, right? And zero forms are always holomorphic or anti-holomorphic functions. All right. So this is guaranteed by something called Riemann-Roch's theorem. Well, I shouldn't say guaranteed. It's forbidden by Riemann-Roch's theorem. If there was, like, basically this being 0, what it would mean is that there would there are no one forms that of this type, right? And so there are some topological invariants that need to be upheld by complex manifolds that is given by Riemann-Roch's theorem that means that this has to be 0. And again, because these two are conjugate to each other, this is also 0. You can also prove this using sheaf cohomology. And we can construct the top degree form in this situation, which gives us this one. Similarly, I mean, we don't have a lot of space here, so let me maybe put this in the next page. For the torus, I'm going to skip most of it. We've understood the main idea. This one is more like we kind of have this idea that tori have more holes than let's say the sphere would have. So we'll see that this in fact instead has all of them are isomorphic to C. So here you have same thing, Liouville's theorem. Here you have dz. Here, so these are constructions. So dz bar, and then here you have dz wedge dz bar. And so this kind of shows that TC has some holomorphic obstruction here. So if we compare CP1 to TC, then we see that H10 is isomorphic to 0 here, and H10 is isomorphic to C here. So there's some holomorphic obstruction on the torus that isn't there on CP1, on the Riemann sphere. So that is the so those are the examples. I just want to point out that there's this interesting symmetry that we can get from here. We can display the Hodge numbers for these using, so C has a dimension of 1, right? So for each copy of C, we'll get a number 1. So dim C is equal to 1 in the complex sense. So if we plot out their Hodge numbers in this pattern, H00, H10, H01, and H11, and then if you had a more like a higher dimensional manifold, complex manifold, then you would have like H02 here, H20, then here you would have H21, and here you have H12, etc., etc. So, and then like maybe you'd get a bigger, this is called a Hodge diamond. Don't know if I mentioned that already. This is called a Hodge diamond. So here you would have H22, which would be your highest number. So for the torus, or for CP1, this is 1, 0, 0, 1. So this is CP1. And for the torus, TC, this is 1, 1, 1, 1. And so these are symmetric off of this axis. It's not as easy to tell with TC, but it's easier to tell with CP1. This is given by the fact that these are both Kähler. This is a bit of a spoiler. These are both compact Kähler manifolds. And so on a compact Kähler manifold, there's a secret extra fact or symmetry, which is that HPQ is equal to HQP. Contrast this with the fact that the on any manifold, on any complex manifold, you have that HPQ partial bar is equal to HQP partial conjugate. This is what's true on every manifold. So this is on every complex manifold. So, but this is only true on complex scalar manifolds. So we will look at why this is true when we get to the lectures on Kähler manifolds and the lectures on Hodge decomposition, because this is very much related to that. I guess the hint is that these are called Hodge numbers, and we're making Hodge diamonds. So everything is a little Hodge right now. And so that's what I will leave you with. This is a teaser for how this might kind of parlay into the theory of Kähler manifolds. As I've been saying every time, and I'll still say it now, everything that we're doing so far is in order to build a Kähler manifold. It's just that Kähler manifolds have so much structure on them that we are spending 10 lectures in order to get to the point where we can talk about Kähler manifolds. And once we talk about Kähler manifolds, we will look at this beautiful decomposition that happens on Kähler manifolds called Hodge decomposition, which required PQ forms, which required all the other results we had so far. And after we do that decomposition, we will look at a very special kind of Kähler manifold called a Calabi-Yau, where something called a metric, we haven't defined a metric yet, but there's something called a Ricci metric that will be 0 on the specifically on the Calabi-Yau manifold, and that's going to cause some more interesting things to happen, and that's going to be the culmination of where we're kind of heading towards in this lecture series. And that's that kind of every single lecture is kind of building some piece of the puzzle in order to be able to talk about those last 3 lectures. Right. So let us end off, now that we've talked about everything I wanted to talk about today, let's end off by recapping and looking at what we're going to talk about next. So we talked about obstructions. We said that obstructions are failures, like some property, the cohomology groups in this case, some property that prevents the local solution to an equation from becoming global, let's say, or from patching into a global solution. We saw that for Diram, this is there exists alpha such that omega is equal to d alpha, given that d omega is equal to 0. And we looked at the geometric interpretation for that fact. And in the Dolbeault case, the equation was the same thing. There exists alpha, but in this case, we looked at partial bar, given partial bar of omega is equal to 0. Then we looked at the Diram cohomology groups, Diram cohomology. We looked at the central idea, which is that which closed forms are not exact, because closed forms detect closed curves and exact forms detect boundaries. So closed forms that are not exact forms detect closed curves that are not boundaries. And then we looked at the de Rham complex and the consistency conditions. Y d square is equal to 0. We looked at what it measures, topological obstructions, what it measures. So in general, this would be real homotopy invariants, which will make more sense if we were studying algebraic topology, where homotopy is defined more rigorously. So then we looked at the comparison with the Dolbeault cohomology group. We looked at the Dolbeault complex. We looked at how we replace closed forms and exact forms with partial bar closed forms and not partial bar exact. And then we talked about holomorphic and anti-holomorphic obstructions, holomorphic and anti-holomorphic obstructions. What does this mean? Well, it's an obstruction in the sense that we can't find global holomorphic functions or anti-holomorphic functions for anti-holomorphic obstructions. And then we looked at Dolbeault's theorem. Dolbeault's theorem. Connection to sheaf cohomology. And this solidified our local to global patching idea. Local to global patching. And lastly, I don't want to move to a new page, so I'll just try it here. So lastly, we looked at two examples. We looked at CP1 and TC, which I call T in the notes, but I thought maybe it's a good idea to call it TC to differentiate it from the real torus. So which would actually be T2. Right. So we are going to the next page anyway. Next time, we will be talking about, so we went down this one thread where from 6 to 7 to 8 to talk about cohomology. So now we're going to be talking about connections and metrics. So now we're in the phase where we're going to be talking about all of this stuff, which is going to be important because we're going to need a churn connection. And from there, we're going to get these things called churn classes. And we're going to have Hermitian metrics, which are going to be needed. Both of these things are going to be needed for Kähler manifolds. Kähler manifolds, again, they're very complicated because they're symplectic manifolds. Symplectic manifolds. They're complex manifolds, and they're Hermitian manifolds. Was that the last one? I think that was the last one. So I'll correct myself if I've gotten that wrong. But they're a trifecta, and so I think the last one was maybe Riemannian manifold. I'll have to check it. So because they have so much structure on them, they have even more things, and each of these three things require so many definitions to even put on the board. So that's why we've taken so many lectures to like try to even talk about Kähler manifolds. So that's what we're going to do next time, is we're going to talk about connections and metrics in order to continue building up tools to talk about Kähler manifolds. So that's it for today. See you guys next time on connections on complex vector bundles.